intimate room for a small early morning gathering, but I'm sure people will start to trickle in once they've registered and gotten stuck into some of the nice food outside. So thanks for coming in on time, and welcome to our full day educational workshop on network neuroscience. And so the goal today really is to give you a bird's eye picture of the field of network neuroscience. And so the first set of talks in the morning are going to cover some of the basic concepts, foundational ideas and methods of the field. And then as we move into the afternoon, we're going to see some talks on more advanced topics and applications and how they can be used to get insights into different aspects of brain network organization. So it's my job today to, in the morning, just give you a very initial introduction to some of the really core basic ideas of the field that will hopefully act as a bit of a foundation for the later talks. Now, before we move on, this year you've probably seen emails, but OHBM is trialling an online system for audience participation. And this allows you to post questions anytime during any of the speakers' talks online. And so if you're not confident or a bit shy about getting up to the microphone, at the end of each talk, either Andrew or I will check for any questions online and we'll ask those on your behalf. So it's a very simple process. You just got to go to that URL there. So that's gmp3.cnf.io. And then you'll see all the sessions listed today, and so there'll be the network neuroscience session. If you press that and then go in and you'll see all the speakers' names, select the speaker, and then you'll be able to type in a question and then hit submit. And so then at the end of the talk, Andrew and I should be able to see that, and we'll try and ask at least one of the questions that have been posed online, in addition to any questions that are asked at the microphones. So, moving on then, why network neuroscience? Well, most of you are probably familiar with the term connectome. It was first coined by Olaf Sporns, Giulio Tononi and Rolf Kötter in 2005, and they defined it as a comprehensive structural description of the network of elements and connections forming the human brain. So the emphasis here, there's two things that are worth noting. So one is a structural description. So we're talking about the anatomical or physical connections between brain regions. So essentially a wiring diagram for the brain. And the emphasis is also on a network description. So we're thinking about the brain in terms of a network. And why would you do that? Well, if you think about it, we can identify networks at all sorts of different levels of resolution in the brain. So we can map networks of molecular interactions that drive synaptic signaling. We can map networks of individual neurons and synapses at the microscale, networks of populations of neurons linked by axonal fibers at the mesoscale. And then at the macro scales that we're typically used to dealing with imaging, we can map large white matter fiber bundles that link broader macroscopic brain regions. And so then, by representing the brain as a network in this way, we have a unified framework for representing all of these different diverse neuroscience data mapped at different scales. So it gives us a common language for bridging scales in neuroscience, and this is really one of the major challenges in neuroscience. How do we bridge these different scales or levels of organization? Now, we're able to do that because we essentially boil the system down to its fundamental elements, and we model the system as a network or a graph of nodes connected by edges. And so in this case, nodes represent some fundamental processing unit of the system, and edges represent some measure of interaction between those units. So in the case of a brain network, a node might represent a neuron or a population of neurons, and an edge would represent some aspect of structural or functional connectivity between them, and we'll go into a little bit more detail about that. Now, the nice thing is, by using this very simple description, we also gain a lot in terms of generality because we can use the same basic model to capture a number of other complex networks found in nature, whether they're protein interaction networks, social networks, technological networks such as the World Wide Web, infrastructure networks such as electricity grids or transportation networks. So then we can really start to conceptualize the brain as just one example of a much broader class of complex systems. And we can borrow tools and techniques from the much broader area of network science to gain insight into brain organisation. So, going back to our network model, so if our main aim is to build a graph or network model of the brain, then we need to define our nodes and edges. And the way in which we do this really constrains how we interpret our findings. So I'm going to spend a bit of time on how we define our nodes and edges. So if we talk about nodes first, in some cases, how we define a node might be fairly unambiguous. So if we had the right data, we could treat each individual neuron as a node. But with brain imaging, we don't normally have access to that resolution, and we don't really have any gold standards for defining nodes, so we need to use different heuristic criteria. And broadly, a good way of defining nodes should satisfy three general criteria. So one is that the nodes should be spatially constrained. So our intuition is that functionally specialized parts of the brain are spatially contiguous, right? So you wouldn't want to define a node that has one bit at the back of the brain and one bit at the front of the brain. We want it to be spatially constrained. Each node should be intrinsically homogeneous, so that means whatever patch of the brain we're defining as a node should be functionally homogeneous within that patch. We don't want to define a node that spans different functional areas or boundaries. And the nodes should be extrinsically distinct, which means that the functions of one node should be distinguishable from the functions of another node. There should be some differentiation between them. So there's lots of different ways of defining nodes, and they satisfy these criteria to varying degrees. The classic example is Brodmann's cytoarchitectonic map, and certainly work by Carl Zilli's and Simon Eichhoff's teams have tried to develop probabilistic cytoarchitectonic atlases for use in the imaging community, although they don't cover the complete brain at the moment. But it's not the only way. We could look at variations in chemoarchitecture, so receptor densities. We can define nodes based on anatomical boundaries such as sulcal and gyral landmarks. We can parcellate the brain at random using parcels of varying sizes. We could generate spherical regions of interest around peak coordinates from some activation map to look at functional ROIs. There's a lot of interest recently in data-driven approaches, so trying to cluster voxels based on similarities in connectivity profiles or other measures. We could use individual voxels as distinct nodes, or more recently the Human Connectome Project team published a multimodal parcellation where they combine data from a number of different imaging modalities to generate a cortical parcellation with over 300 regions. Now, I'm not going to comment on which approach might be better or worse. I think it very much depends on the question you're interested in, but in general it's good practice to try and replicate your findings across at least a couple of different parcellations, just to make sure that your results aren't driven by the idiosyncrasies of any particular scheme that you've chosen. So that's nodes. Now let's talk about how we go about defining edges. And so when we're defining edges, we're really talking about how we measure connectivity between nodes. And so that means we've got to think about different aspects of brain connectivity. And broadly, we can distinguish three classes of brain connectivity. So there's structural connectivity, which is really the physical or anatomical connections between regions. And so this is intrinsically directed. Each axon has a source and a target. But with imaging, we can't really resolve that directionality, so a lot of our estimates are undirected approximations. Then there's functional connectivity. And so in this case, we record some physiological signal from each region. So we've got a time series of signal fluctuations in each node. And then we compute some measure of statistical coupling between those time series, most commonly in the form of a correlation, but it could be some other measure such as mutual information. It could be a directed measure. It's really up to you. And the final type of connectivity is what's called effective connectivity. And so this is the influence that one neuronal system exerts over another. And so the key thing here is that we're making inferences at the neuronal level. And so if we have a measurement technique that's an indirect marker of neural activity, such as, say, fMRI, then we need some kind of model or mapping between that measured signal and the underlying neural activity that generated it. And so the most famous example of this is something like dynamic causal modelling, where we're trying to specify causal interactions between neuronal populations based on the measured fMRI signals, and there's a model that couples the fMRI signal to the underlying neural dynamics. And so the main distinction between effective connectivity and functional connectivity is estimated at the level of the measured signal. Effective connectivity tries to make inferences at the level of the neuronal population. Now, there's lots of different techniques for mapping structural and functional connectivity, varying from electron microscopy and track tracing to invasive electrophysiology, calcium imaging, intracranial EEG, and so on. I'm going to focus on the two main techniques that are used in studies of humans with brain imaging, and so that's diffusion MRI and functional MRI. So we'll start with diffusion MRI. Now, most of you are probably familiar with the basics of diffusion MRI. The idea is that we're measuring water diffusion in the brain, and axons act as barriers to that water diffusion, so the water diffuses in a trajectory that runs parallel to the axon, and so we can use that information to track the path of white matter bundles in the brain. There's lots of different ways of doing this, but broadly these are techniques that we call tractography, and we can class most of these techniques as either deterministic or probabilistic tractography methods. And we can apply those and generate sort of whole brain maps of white matter fibre bundles in the brain. Now, there's lots of different models, ways of modelling the diffusion signal, and for reproducing tracks using different tractography algorithms. Again, I won't go into the pros and cons of these different approaches, but in general there's a trade-off between sensitivity and specificity. So here there's some data of some tractography from a couple of regions of interest, and on the x-axis is the specificity, on the y-axis is the sensitivity, and each point represents a different algorithm. And so in general what you see is that techniques that are very sensitive, that reconstruct a lot of fibres, are also prone to false positives, whereas techniques that protect you against false positives, so they're quite specific, are also prone to false negatives. So it's a bit of a trade-off at the moment that we haven't fully resolved, and so the technique you choose will depend on how prone you are to either false positives or false negatives. Now, once we map our tracks, we typically estimate connection strengths between two regions, most commonly as either the number of streamlines that we reconstruct between two areas, or some average measure of tract integrity across the tract. Now, these are pretty indirect measures, so it's important to keep that in mind. You know, streamlines are not the same as axons, so that's a very coarse approximation of something like axonal number or density. And measures such as fractional anisotropy, mean diffusivity, although commonly used as markers of white matter integrity, can be influenced by a lot of other things. And for people that are interested, I highly recommend this article by Derek Jones that really goes into a lot of the details and the limitations of these measures. Now, there is a lot of work that is trying to develop more biologically or physiologically grounded measures of connectivity strength from diffusion MRI, and hopefully they'll start to receive a greater uptake over the next few years. So now I'll move on to functional MRI. So typically we will record our fMRI signal in each node, and then we want to compute some measure of coupling between pairs of nodes. So it could be correlation, partial correlation, mutual information, whatever our desired measure is. And then from that, we do that for every pair of nodes, and then we can build our graph model of the network. Now with fMRI, we can measure dynamics broadly under three classes of conditions. So one is a stationary resting state design. So we put people in the scanner, they're not doing anything in particular, we record activity over a period of time, and then we summarize those dynamics with a single value, such as a correlation coefficient. In recent years, there's been a lot of interest in looking at dynamic patterns of functional connectivity. So most commonly, we could use like a sliding window approach where we bin the data into separate time bins and construct a network at each bin. So then we end up with a time series of networks. And so we can look at how the network evolves through time. And in this case, we need to use appropriate statistical models to ensure that the fluctuations we see are not just a matter of chance. And we can also measure functional connectivity during a task. Now, during the task, the stimuli are driving activity in a particular way, and so it's important to have a model that tries to account for the influence that the task is having on functional connectivity, because generally we would want to isolate task-related functional connectivity from more background task-related or intrinsic processes. And there are some references there for some studies that try to do that. Now, I'm just going to point out that fMRI pre-processing is a very loaded and controversial area, and there are a lot of different pipelines, but the pipeline that you use does matter. So generally we acquire our data, we pass it through a processing pipeline, we extract our signals, and off we go. Now, what goes into that box, there's lots of different choices and options. And just as an example, this is a study we ran recently where we looked at some 16 different motion denoising pipelines and compared their performance. And there's quite a lot of variability. So the shorter the bar is in this graph, the better the technique is at removing motion. And you can see there's a lot of variability. So for some techniques, typically the simplest and most widely used, over 70% of connections still have some residual contamination by motion. Right, so it is important to very much consider the pre-processing technique you're having, because it will influence how you interpret the findings. And certainly if you then go and do some case control comparisons, such as healthy controls versus schizophrenia, you might see differences under some processing techniques and no differences under others. And even when you do find differences, they might not necessarily be the same. So this is, the top is one processing pipeline, the bottom is another. The details are not so important. But if you just look at the anatomical maps, on the right we have connections that are reduced in patients. In the top, I would conclude that most of the changes seem to be in the frontal cortex, whereas if I use the bottom pipeline, I'd say, oh, well, most of them are sort of in the middle of the brain. And if we look at the left, the blue represent increased connections in schizophrenia. In the bottom, most of those connections are in the back of the brain, whereas in the top, they're mostly somewhere in the middle of the brain. Right, so the pre-processing pipeline that we use is going to have a big impact on the conclusions that we draw from our data. The measure that we use to estimate functional connectivity will also play an important role in how we interpret our data, because certain measures can introduce biases into our measures. So most commonly functional connectivity is estimated using the simple correlation coefficient, but that turns out to be quite a biased measure. So just to illustrate the point, imagine we've got two different networks here, and so I've mapped the structural connectivity. In the top we've got an open triangle, so the bottom node connects to the top two, but they're not connected to each other. And then in the bottom we've got a closed triangle, so each pair of nodes is connected. Now if we use a correlation coefficient to measure functional connectivity, we're going to do well in the bottom case. We'll find some functional connectivity between all pairs of nodes. But in the top case, we're going to find some non-zero level of functional connectivity between the top two nodes, even though they're not directly connected structurally. This is because mathematically, with correlations, if A correlates with B and A correlates with C, then B and C also have to correlate with each other to a certain extent. So correlations have this tendency to close off triangles. And you can run some tests to see if this introduces a bias, and indeed it does. It turns out that networks constructed using correlation coefficients are more clustered than you would expect by chance. And so clustering is just a measure of the number of closed triangles there are in the network. And using the correlation coefficient ends up in a much more clustered network than it should be. So all well and good then, you might say, well, in that case we should use a partial correlation because that's much better at estimating the direct pairwise interactions between regions. And so in the case of an open triangle, it will probably do pretty well. It probably won't find functional connectivity between the two unconnected nodes. But in the case of a closed triangle, it's a little less clear. And the result you get depends on a number of different factors. And it turns out if you run some tests, these networks tend to be less clustered than chance. So we have a bias working in the opposite direction. So partial correlations tend to overcorrect or over-penalize. Now there are techniques that you can use, for example, regularized inverse covariance methods that have tunable parameters that allow you to kind of vary between a full correlation and a full partial correlation that you could play with to resolve this. But this is just to point out that the measure that you use to estimate functional connectivity can indeed affect the final results that you get in your network analysis. But assuming we're happy with all that, we've defined our nodes, we've measured some aspect of structural or functional connectivity between every pair of nodes, then it's time to build our network. And we do that by representing all the connections in the form of what's called a connectivity matrix or an adjacency matrix. And mathematically, this is equivalent to a graph model of the network. So I'm just going to dwell on this a little bit. So say we zoom in on a connectivity matrix. In this matrix, each row and each column represents a different node, and each element represents the type and strength of connectivity between nodes. So if we go to row 1, column 2, there's a value of 0.8, so the correlation between nodes 1 and 2 is 0.8. Between 1 and 3, it's 0.45, and so on. Now you can see along the diagonal, there's that dark bar, that's essentially the connectivity of each node with itself. So this is a correlation network, so we just set it to 1, or optionally it's set to 0. And so everything above the diagonal is called the upper triangle, and everything below the diagonal is called the lower triangle. Now, if we have an undirected network, say a correlation network, then the upper triangle and the lower triangle are going to be symmetric. Right? So if I look at row 1, column 2, I get 0.8. If I look at row 2, column 1, I get 0.8. Right, so that's just the same as saying it's an undirected network, so whether I go from node 1 to node 2 or vice versa, I get the same value. I'm not distinguishing directionality. Now, if we mapped connectivity in a directed network, then we would have different values in the upper and lower triangles. And it would depend on how we list it. So some people list outgoing connections down the columns, some list them going out the rows. But in those cases, the matrix is asymmetric, right? So the value of element ij is not necessarily the same as the value of element ji. Now, once we map a network, we might get something like this. So this is a correlation network. So in this case, correlations values range between -1 and 1. So we get a non-zero value for every element. So it's a weighted network. It's common to apply a threshold to try and distinguish noise from signal. So in this case, we might set all the values below a certain threshold to 0, shown by black here. And then often, many people also binarize the network. So they set any remaining connections to a weight of 1, so they all have the same weight. And so in a binary analysis, we're really just concerned about the pattern of connections between regions. We're not considering variations in connection strength. So we're only emphasizing a very specific property, but that comes with a loss of information. Now, some methods for network construction come with its own intrinsic threshold. So for example, if I generate a diffusion MRI network, I'm not necessarily going to find a tract between every pair of regions. In this case, if I use a deterministic tractography algorithm, which is less prone to false positives, but perhaps susceptible to false negatives, I can map 28% of connections. If I look at the same data with a probabilistic algorithm, which is more sensitive, but perhaps more prone to false positives, I reconstruct 60% of connections. So the method we use also affects the threshold that we're going to be analysing the data with. Now, this is just to show the equivalence between matrices and graphs. So up the top, I've got a graph of 6 nodes, and down the bottom, I've got the corresponding matrix representation. So you can see that node A is linked to E and C. And so if I go down to the matrix and I look at row A, I go along to column C, there's a 1. I go to column E, there's a 1. And because this is an undirected network, I can go to the lower triangle and find the same. So if I go down column A, there's a 1 in row C and a 1 in row E, right? So the matrix is symmetric. If we have a directed network, say like this, in this case in the matrix we've listed outgoing connections down the columns. So you can see that A has 2 outgoing connections to E and C. So I go down column A, row C there's a 1, row E there's a 1. And then if I look along row A, there's a 1 for column C because C sends a projection back to A, but there's nothing else, right? Because A has no other incoming connections. So in this case, you can see how that symmetry is broken, all right? So the upper triangle is not the same as the lower triangle, and so that's representing our directionality. If we want to represent weights in a graph, that's typically shown by changing edge thickness, and in a matrix we can use colors or just actually show the different values, and we can do the same for a directed network, to have a weighted directed network. So we've got all these networks, so you might say, well, what kind of graph then best represents the brain? Well, we could start with a simple binary unweighted network, but we know that connection strengths vary quite a bit. Recent data suggest over several orders of magnitude, so we might want to account for that and look at a weighted network. As I mentioned earlier, each connection has a source and a target, so we want to account for directionality. We also might want to consider heterogeneity across nodes. So different brain regions vary in terms of their cellular composition, patterns of gene expression, functional role, and we might want to account for that in some way. And so there are techniques for doing so, but they just haven't been used a lot. We also know that edges are not all the same. Some are inhibitory, some are excitatory, and again, we might want to account for that in some way. So really what we're talking about is some kind of hybrid graph. We've got direction, weight, and edge and node heterogeneity. And this graph should really evolve through time. So functionally, from milliseconds to minutes, and both structurally and functionally, on developmental timescales ranging from days, months, and years. So how are we doing? Well, most studies do the simplest possible thing, which is looking at binary undirected networks. And that's certainly what most of the field has done to date. Increasingly, people are starting to use undirected weighted graphs. And with some nice track tracing data sets, we're also starting to see some good directed connectomes become available. And in certain cases, we can also start to look at different types of edges, but that is quite niche at the moment. And certainly node heterogeneity is not something that has been looked at extensively. So there's still quite a lot of room for improvement in terms of enhancing the biological validity of our graph models of the brain. And part of this is due to a limitation of our techniques. Things like node and edge heterogeneity are quite hard to resolve with our imaging methods. So as the techniques develop, we should be able to develop more refined and nuanced models. But assuming we're happy with our graph model of the brain, the next step is analysis. And broadly, when it comes to brain networks, there are two classes of analysis we can do. So one is looking at connectivity. So this is really focused on studying variations in the strength and type of connections between brain regions. And the other is focused on topology. So in studies of topology, we're really concerned with how connections are arranged with respect to each other. And so this is really where we use the mathematics of graph theory to try to uncover underlying organizational principles of how the network is arranged. And so really the rest of today's workshop is going to be talking about or expanding on these different types of analyses. So Andrew Zaleski will be talking about statistical methods for looking at connectivity. James Roberts is going to talk about null models for network analysis, which are really important for statistical inference on networks and as a benchmark for comparing different networks. Then we're going to move really into the realm of topology, where Bratislav Misic talks about communication models, so different models of how signals might propagate through the network. Martin van den Heuvel is going to talk about concepts such as centrality, hubs and rich clubs. And Rick Betzel is going to talk about modularity, so thinking about how we can decompose the network into functionally specialized subsets of nodes. Then we're going to move into more advanced topics. So these are kind of really frontier areas or emerging areas in network neuroscience. And so Emma Towson is going to talk about how control theory can be applied to networks. Dragana Pavlovic is going to talk about stochastic block models, which provide a statistical framework for gaining insights into network organization. And Sizemore is going to talk about algebraic topology, which is a kind of new hot area for gaining insight into network topology. And then Joanna Cabral is going to talk about physiological models of dynamics taking place on the network, so trying to simulate patterns of brain activity on network structures. So hopefully that'll kind of give you a nice, fairly comprehensive view of the different things that are happening in the world of network neuroscience. But before we move on, I'll just close by summarising this introductory talk. So hopefully I've convinced you that graphs provide useful models of brain networks, and the real power is in its simplicity, and it offers a unified framework for representing diverse kinds of neuroscience data acquired with different measurement techniques and at different scales. There's lots of different ways of defining nodes and edges, and it is important to think about the ingredients that go into the cake, and because that really determines how we interpret our findings. We can generate brain networks that are either directed or undirected, weighted or unweighted. There is also the potential to account for node and edge heterogeneity. This is an area of ongoing development. And we can analyse brain networks in terms of connectivity or topology. And we can extract metrics that characterise properties either at the level of individual edges or individual nodes, subsets of edges or nodes, and at the level of the entire network. And so it is quite a remarkably flexible framework. So I'll just close by listing some resources. So in the top left, there's some general texts on network science. So this is more broadly the physics of complex networks in general. The text by Mark Newman and Albert Barabashi are really excellent. There's some books and review articles on network neuroscience. There's some software there for anyone who's starting out you can check out. There's a textbook that Andrew Zaleski, Ed Bullmore and I wrote on network neuroscience that's available through Amazon or Elsevier. And there's also a new journal called Network Neuroscience, published by MIT Press with Olaf Sporns as the editor-in-chief. So if you are active in this area, please do consider sending your work our way. And if you've got any more questions, please feel free to get me at those contact details. But thanks for your attention.